Hi, I'm Wang from USS Lab, Zhejiang University. Today, I'm going to talk about our recent work, Volttack, control IoT devices by manipulating power supply voltage. IoT devices are growing rapidly in a variety of scenarios, such as smart home, robot, transportation, and industry, where all interaction with the physical world is the foundation of critical IoT systems. Sensors and actuators are key interfaces between the physical world and IoT devices. Correct sensing and actuating is critical for IoT devices. As we illustrated here, the IoT devices are mainly composed of four modules. Sensors perceive the environment, CPU makes decision, actuators control the physical world, and the power supply output voltage rails to power the other modules. So, what can go wrong during use? The first one is interfering from the environment. Previous work, such as Dolphin and Walnut, has showed malicious physical signals can tamper with IoT devices. Second, previous work, such as Shelter Trust, has showed the risk of malicious hardware. Third, previous work, such as Pandemic, has showed the firmware can be compromised and cause malfunction of IoT devices. And the power supply module is indispensable and vital for IoT devices, but it's unclear whether power supply module can be exploited for attacks. Since it's very important for IoT devices, designers have made great efforts to improve the power supply module reliability. First, designers use power supply rejection ratio, abbreviated as PSRR, to describe the ability of a power supply module to reject fluctuations. They have increased PSR against the noise that are likely to present. Second, designers added filters to remove unwanted noise. Moreover, they conduct EMC testing to ensure stability of IoT devices in electromagnetic environment. But what is the reality? Do all these designs work as expected? According to our observation, the answer is no. First, for the power supply module, we expect a good noise rejection performance. That means high PSR over the full frequency range. But by checking the datasheet of state-of-the-art products, we found the PSR worsens with the increase of frequency. Second, filters are composed of capacitors and inductors and are used to remove unwanted noise. However, due to the non-ideal characteristics of these components, real filters may not be able to remove high-frequency noise. Third, the EMC testing focuses on the frequency range of 150 kHz to 80 MHz. However, according to our experiment findings, power noise in the uncovered range can also tamper with IoT devices. In this work, we investigate what these features can lead to. We suppose the attacker may be a malicious employee, a guest, a maintenance worker who has a one-time access to the power supply source. She can either add attack devices to the power distribution cabinet or the power socket, or replace the original battery. Then she can inject manipulated signal and achieve malicious consequences, such as spoofing the sensor perception or controlling the actuator action. To understand the principle of how power supply signal affect IoT devices, we have two questions. First, how can malicious signal go through the power supply? Second, how does the malicious signal affect the output of sensors or actions of actuators? The challenge is, what is the underlying principle that affects most IoT devices? To overcome this challenge, we study from the perspective of electronic components, which constitute the IoT devices. The elementary electronic components are the smallest unit of circuit, such as resistors. They are connected in different ways and constitute compound electronic components, which can perform complex functions. We categorize the power supply's effect on elementary electronic components into two basic mechanisms. The first one is interfering with input signal. Normally, the input signal is processed by the components and gets to the output. We consider the power supply signal superimposed on the input. In this case, it can affect the output similar to how input signal does. The second one is modifying the characteristic. For components requiring the power supply, the input signal can control the on and off state of output signal. In this case, the power supply signal drives the electronic components. It can change the input and output relationship. For example, manipulated signal can keep the output in the on state regardless of the input signal. On this basis, we want to see if these mechanisms apply to compound electronic components. By doing simulation and experiments, we observe similar effects on compound electronic components, such as operational amplifier. Normally, the input signal is amplified and gets to the output. The power supply signal can affect the output with the transmission gain. The power noise is expected to be eliminated, so ideally, the transmission gain should be as small as possible. However, we find it varies with signal frequency. And around 1 MHz signal can affect the output without being attenuated. Now that we understand how power supply signal affects the electronic components, we design and implement Volttack on 6 sensors and 3 actuators. There are 4 sensors used in automobile brake pedal, environmental monitoring sensors used in industry process control, servos used in robot arm, and a valve used in liquid flow control. For each one, we repeat the experiments 10 times on 5 instances. First, we consider an automobile brake pedal. In emergency braking, the driver gives it 200 newtons force, and the sensor output is also 200. Supposing the braking distance is 20 meters, the original power supply voltage is 24 volts. By injecting a 342 MHz signal with an amplitude of 2 volts to the power supply module, the attacker can change the sensor output to 100. Then the braking distance will change to 40 meters. It is doubled, and this may lead to a car accident. Second, we consider the disinfectant flow control in the water treatment. Suppose the valve opening is 25% and appropriate amount of disinfectant is flowed into the water tank. By injecting a 75 MHz signal with an amplitude of 0.5 volt to the power supply module, the valve opening changed to 38%. Then, excessive disinfectant will flow into the water tank. This may lead to poisoning water. Here comes the next important question. Is Volttack a real threat? Then we implement Volttack in the real world with 3 methods. First, we fabricate a malicious battery and replace the original one. Second, we connect the attack devices to the power socket. To avoid the damage of high voltage power source to the attack devices, we customize a coupler. Third, we place a current injection probe on the power cable to couple the attack signal to the power supply. Here we consider a valve used in industrial coolant flow control. We connect the attack devices to the power socket using the customized coupler and attack the valve on the right. The initial opening is 47%. We start attacking and the opening change to 27%. This may lead to insufficient coolant and an overheating explosion. To mitigate the threat, the designers can either improve the noise rejection performance of power supply module or monitor the power supply voltage to detect the attack. What we'd like to show through this work is the power supply module can be an attack surface and cause serious consequences. We call for attention in designing power supply modules. For example, improve the noise rejection performance for future devices and monitor the power supply voltage for legacy devices. That's all of my talk. Thanks for listening.
Questions?
Hello, good presentation. On your research, did you determine if individual devices had to be attacked at a different frequency to get the outcome that you wanted? Or did you find a silver bullet or a magic frequency that seems to work for everything?
Yeah, we find that different devices have different different attack frequency. For example, for the force sensor is 342, and for the valve is 75 megahertz.
Great, thank you. This is excellent work. I love just looking at the physical component of things. But I'm wondering whether the modules are what you should be looking at. The modules are always part of a system, so it might be the component can respond to these high frequencies. That's why you have capacitors, right, as frequency filters in the power supply. You always condition your power supplies in a full system. So what I ask is, in the context of these modules you looked at, what do their data sheets say about the surrounding power supply filtering circuitry?
You mean what's the explains the data sheet?
What I mean is you have a power supply, but usually when you integrate your power supply into a system, you put surrounding capacitors and inductors and resistors in order to condition the supply for what your components need. And so I'm wondering if you looked at then, if you incorporate those filtering circuits, what happens?
Yeah, the filter the designers most applied is a passive filter or active filter. And we find the capacitors can be equivalent to a combination of capacitor, inductor, and a resistor. The result is the passive filters may not be able to remove the high frequency noise. And for the active filter, as shown in the experiment, the active functional amplifier can be attacked by the high frequency signal, so it fails too.
Thank you.
Other questions? Okay, let's thank the speaker.
Thank you.